right, so let's have a look at this next one. It says a study of antelope population in a wildlife park has shown that antelope regularly move between 3 locations. The state matrix shows the population of antelope after N months. So this is, just remember, state is month to month. And then it says here we've got the formula. So once you see that, you know you've got the extra. You can't use the power trick. You're going to have to use it recursively. And they've given us a whole heap of information here. So we've got transition, we've got the D, and we've got also A3. Now, it says the number of antelope in the west location 2 months after the study began was found to be, and so they told you want A2. So if you think about it, we have to, if you were finding A2, we would actually need the one before, which is A1. We don't have that. We've got A3. So what we want to do, if you think about linking it up, and I'm just going to do it down here, if you think A3 was found by using the formula, which would have been the transition times A2 and minus D. Now, when you think about what you've been given, you've got this, you've got this, you've got this, and I need this. So what we're going to have to do is a little bit of rearranging. Now, first of all, if you tell, sometimes it's easier if you think about what happened here. So when you look along here, we had the transition times A2, then we minus D. Remember, the last thing you say is the first thing you move. So over here, we're going to move this guy over there. We want to try and get A2 by itself. So we'll move that. I'll just do it in steps. So I'm going to have D. D's going to become plus there. And then we've left this here like that. Okay, so that's the first step. But remember, we want to get A2 by itself. So I want to move this. Now it's timesing. What do we do when we move a timesing over an equal sign? So we need to do the inverse. Now, we need to do the inverse of what's already happened over here. So we need to pop that in brackets. So you would do that first. So now, is the T at the front of the one that we don't know? Yep. So when we do the inverse I'll do it in green so you can see. The inverse needs to be at the start here. So we're going to do, and you don't have to do it step by step in your calculator. You can just actually do it like this, as long as you put it in brackets. Like, tell the calculator you want to do that adding part first, and then you want to times it by the inverse. And then you can see we'll end up with A2. So if I go to the calculator and I just find that, I believe this is, sorry, I'm just going to double check that this is the right matrix. Yep. Okay, so we want to do the transition. No, what do we want to do? We want to do the transition to the power of -1. Then I want to times it by, I'm going to open my brackets. I want to do D. What was D? The 50-50? Was it? Yeah. D was that one? Yes. And then plus is the 116, that's A3. Close the bracket and press enter. So let me double check that was, yep. Okay, so we end up with 1630. What was that? 1630, 280, 8, and 2. Oh my God, I've bad memory. Okay, and we want the west one, which was the last one. So the answer is E. All right, question 8. An airline parks all of its planes at Sydney Airport or Melbourne Airport overnight. The transition diagram shows the change in location of planes from night to night. There are always M planes at Melbourne Airport, and they're always S planes at Sydney Airport. So of the planes parked at Melbourne Airport on a Tuesday night, 12 had been parked at Sydney Airport on Monday night. So what you think about there, they gave us a little bit of information. They said if we were at Sydney on when it was at Sydney, and then they went to Melbourne to Tuesday, so that was in one day, there was 12 that went that way. Okay? So, but what you have to, so you could find out, so if you go 12, you go Sydney to Melbourne is, if you look at up here on the transition, so where's that? Sydney to Melbourne is 0.48. So you know 0.48. So if I said this is Sydney and this is Melbourne, 0.48 of Sydney equaled 12. All right. So no, was that right? Of the planes parked at Melbourne Airport on a Tuesday, 12 had been parked at Sydney on Monday night. So, yep. So Sydney, so 0.48 of that equals 12. So if you do that, you go 0.48 times S equals 12. So you could do solve if you like. And you get, yeah, good. Get 25. And you get S equals 25. So that's told me what Sydney has, but it says how many planes does the airline have? So I still need to find what Melbourne have. But the key was up here. It said that there was always M planes parked at Melbourne and always S planes parked at Sydney. So what happens if 12 go out? If 12 go out, if they're always got the same, that means 12 must go in. Okay? And that's what you're saying. If they say they're always the same, what goes out must come in. So now you got the other statement I can use up there. Well, if 12 went out, we know, therefore, then we can say from Melbourne to Sydney, we had 12 as well. But if you look at that one's percentage, that's 0.2. So then we can say, all right, 0.2 of Melbourne has to equal 12 as well. And then you do 0.2 times M equals 12. And you can do solve, comma, S. So you equal M equals, M equals 60. So the total airline, they have 85. Okay, so 10,000 trout eggs and 1,000 baby trout, 800 adult trout are placed into a pond and establish a trout population. So the eggs can either, you can have eggs, they may die, or they can become baby trout, or they become adult trout. And here's a transition to show how they are working. So they told us, so up here, we were given an SO because they said to begin with. So we can see, obviously we got eggs, baby trout, adult trout, and then die. So in the beginning, we got 10,000 eggs, we got 1,000 baby, 800 adults, and in the beginning, none have died. So we're going to put 0. So that was probably something you had to sort of think about. And then it says, here's the transition, and it says use this transition matrix to determine the number of eggs in the first year. So that's going to be S1. So we just want to know what E is. So I'd probably just pop it into the calculator. So if we look, we've got the transition, and we want to times it by SO and press enter. What did it ask? How many eggs died in things? So we got 7,150.
No, isn't that total deaths?
determine the number of eggs in this population that will die. Oh, just eggs, sorry. Yeah, so eggs to die is 0.6 of 10,000. Yeah, you were right. Equals, sorry, that was 6,000. Yep, that's good. I didn't read the question very well there. And then it says complete the diagram below. So you have to link up all the things. So if you look at, they've done, if I look at E, they've done the 40 to B and the 60% to D. If I go to B, we want to have 25% out here. We want 50% here. The probably the biggest error here was people probably not writing it as a percentage. Make sure you put it, because that's what they've done, so we need to keep it the same. Okay, and there's that one. Okay, so the initial state matrix for the trout population is written there. So then it says using this rule here. So this was just an older question. They used to write it like that, but we'll now always see it written with the T times SN. So that just means we can get the next one using the time before. So it said to determine S1. So we would be using, just like we did here, actually, we did the transition times SO, and this was what we saw S1 to be. So we got 0, 4,000, 650, and 7,150. So it just says determine S1, so we leave it in the matrix state, and then it says the number of adult trout predicted to be in the population after 4 years. So remember, this up here is a year-to-year transition. So we can use the power trick here because there's no extra one. So we could say if we want to find S4, we will just do the transition times, I'm going to say 3 because we've been given S1. So let's just check what they said for the first year. Yeah, so we said that was what we had in the first year. So S1 is actually after 1 year. So then after 4 years will be S3. Or we could use SO to the power of 0, whichever. So let's go have a look at that. So I'm just going to highlight that again. Because that's SO in there, I'm going to raise it to the power of 4. And there we go. And I'll just write it over here. So we had 0, 0, 3, 3, 1. I'm going to round because they're trouts, so I'm not going to have a decimal trout. And 1, 1, 4, 6, 9, I think. So if you add them up, it'll be the same amount. And it said the number of adult trout. So remember, this was eggs, baby, adult. So we can say we had 331. Okay, the transition predicts in the long term that all the eggs and baby trout and adult trout will die. How many years will it take for all the trout to die? That is when the adult trout first predicted to be less than 1. So you just actually have to just keep on trying in your calculator. So just watching, we want that 331 to be 0. So let's have a look if we keep rounding up. So we go to the power of 5. It's halved there. So let's have a look. Maybe power of 6 you just got to keep going through, unfortunately. So it must happen pretty quick because they don't make you keep testing for ages. So there's 82. I reckon maybe one more. So let's keep checking. 7. No, this is getting annoying. But anyway, let's go. Okay, so by the number 13, we got it down to 0.6. So that's under 1. So we're going to say that's less than 1. So we'll know. So it was the power of 13. So after 13 years for that one. What is the largest number of adult trout that is predicted to be in the pond in any 1 year. So you just need to go check the third number down, and because you've seen it go to